Everything around us is moving, all the time. I mean, even if you're sitting perfectly still right now, you're actually on a planet that's spinning and flying through space. So how on earth do we make sense of all this movement? Well, in this explainer, we're going to figure that out together. We're going to build the science of motion right from the beginning, starting with one simple but kind of mind-bending idea.
So, here's our plan. We're going to build up our understanding piece by piece. We'll kick things off with the big idea that all motion is relative. Then, we'll get our hands on the basic tools, things like distance, speed, and acceleration. And finally, we'll see how we can actually draw a picture of a journey using graphs and even use some cool equations to predict the future. Ready? Let's go.
All right, first things first. Before we can even start talking about how something is moving, we have to agree on something that isn't moving. And that sounds pretty simple, right? Well, as you're about to see, it's actually a little trickier than you'd think.
So let me ask you a question. Are you moving right now? You're probably thinking, no, of course not. I'm just sitting here. But are you? I mean, you're on planet Earth, which is spinning like crazy and also zooming around the sun. See, the answer completely depends on your frame of reference. Think about it. If you're on a bus, the person sitting next to you seems totally still. But to someone standing on the side of the road, both of you are whizzing past. And that's exactly why physicists use something called a reference point. You can think of it as our anchor, our "you are here" map pin that we all agree on. Without it, describing where something is pretty much impossible. If I just say a school is 2 kilometers away, that's totally useless, right? 2 kilometers from where? But if I say it's 2 kilometers north of the railway station, now you have a clear picture. The railway station is our reference point.
Okay, so now that we have our reference points sorted, we can finally start measuring a journey. But what exactly are we measuring? Are we talking about the entire winding path you took? Or just where you ended up compared to where you started? It turns out these are two very, very different things.
On one side, we have distance. This one's simple. It's the total ground you covered, what your car's odometer would read. Every single meter. It's what scientists call a scalar quantity. It's just a number, like 10 kilometers. But then we have displacement. This one's a bit smarter. It's the direct, straight-line measurement from your start point to your finish point. It doesn't care about the scenic route. And because of that, it has both a number and a direction. It's a vector. So it's not just 10 kilometers, it's 10 kilometers east.
Let's look at this diagram to make it super clear. Imagine an object starts at O, travels all the way to A, which is 60 kilometers away. Then it turns around and comes back 25 kilometers to stop at point B. So what's the total distance it traveled? Well, it's easy. 60 kilometers out plus 25 kilometers back. That's 85 kilometers in total. But what about its displacement? Well, where did it end up compared to where it started? It's at the 35 kilometer mark. So its displacement is just 35 kilometers. See the difference?
So, here's a fun question. Could you travel a really, really long way and still have a displacement of 0? And the answer is absolutely. Think about running a full lap around a racetrack. You might have run 400 meters, but because you end up right back where you started, your final displacement is 0. You haven't actually been displaced from your starting position at all.
All right, so we've got the where sorted out. The next obvious question is, how fast did it get there? And just like before, this brings us to another important pair of ideas that sound similar but are quite different: speed and velocity. And you might have already guessed it. This is totally related to distance and displacement. Speed is the simple one. It's connected to distance. It's just how fast you're going, found by dividing the distance you traveled by the time it took. Velocity, on the other hand, is linked to displacement. So it's not just about how fast you're going, but also in which direction. When your car's speedometer says 60 kilometers per hour, that's its speed. But if you say it's going 60 kilometers per hour north, now you're talking about its velocity. Let's be real. In our world, things hardly ever move at one steady velocity. We speed up, we slow down, we turn corners. We need a word to describe all of that change, and that word is acceleration. Now, this is a big one, so listen closely. Most of us think acceleration just means speeding up, but in physics, it's any change in velocity. So yes, hitting the gas pedal is acceleration, but hitting the brakes is also a type of acceleration, just a negative one. And here's the really cool part. Because velocity includes direction, even turning a corner at a perfectly steady speed is a form of acceleration. Why? Because your direction is changing.
And we can even split this into two types. First, there's uniform acceleration. This is when the velocity changes by the same amount in every equal time period. nice and steady. A perfect example is a ball falling due to gravity. Then there's non-uniform acceleration, which is basically life. Think about driving a car in traffic. You're constantly speeding up, braking, speeding up again. Your velocity is changing all over the place. That's non-uniform.
Okay, I know. All these numbers and definitions can feel a bit abstract. So what if we could actually see motion? Well, we can. By turning data into a graph, we can literally see the story of an object's journey.
So take a look at this table. It's just a bunch of numbers showing how far a car has traveled over 12 seconds. Kind of boring, right? But trust me, there's a story hidden in those numbers, and we're about to bring it to life.
And here it is. When we plot that data, we get a picture. Now, if the car were moving at a constant, steady speed, this would be a perfectly straight line. But look, it's a curve that's getting steeper and steeper. What that curve is telling us visually is that in every new time interval, the car is covering more and more distance. That beautiful curve is the picture of acceleration.
Okay, so we can describe motion, we can even draw it. But now for the really powerful part. What if we could actually predict motion? By combining all the concepts we've learned, we can create some amazing equations that let us do just that.
Now, don't be scared by all the letters. These are our 3 key formulas. They just connect 5 basic things: the initial velocity u, the final velocity v, the acceleration a, the time t, and the distance s. And the beautiful thing is, if you know any 3 of these values, you can use one of these equations to solve for another one. It's like a calculator for motion. Let's see it in action. A car speeds up from 18 to 36 kilometers per hour, and it does this in 5 seconds. The first step is always to get our units right, so we convert everything to meters and seconds. Now we know the starting speed, the final speed, and the time. We just pop those values into the first equation, and it tells us the acceleration is 1 meter per second squared. Then, we can use that answer in the second equation to find out exactly how far the car traveled while accelerating: 37.5 meters. No guesswork needed.
And just to bring that idea of acceleration home one last time, look at this stone being swung in a circle. Its speed might be perfectly constant, but because its direction is constantly changing, its velocity is constantly changing. And what did we say a change in velocity is? That's right, it's acceleration. So that stone is always accelerating, even if its speed never changes.
So there we have it. We've built our entire toolkit. We started with the simple idea that motion is relative, and now we have a precise language to describe the world. Instead of just seeing something as fast, you can now see velocity. Instead of slowing down, you can see acceleration. The next time you're in a car that turns a corner, or you watch a ball fly through the air, you'll see the physics behind it. You've learned the language of motion. So how will you use it to see the world differently?